Sorry, my computer got suddenly shut down due to the overheat. So we will continue. So today I will go through these kind of examples. So that is, we will load the small model like this and try to apply some techniques and try to get some results. So we will do this exercise in a little while. So we can generate something like these kind of plots. So the software will generate the plots like this, but it's up to you to decide why there is a red area here, why there is blue area here, so why we get a bend here, so why we get something like a ellipse shape at the end of the simulation. So those things are the difficult questions to answer. So we have to do some fine tuning and see whether the results are going to converge. We have to do some remeshing like this. So starting from a big element, these are called elements, and go to the small elements like this and try to fine tune the things. So I will go through this example with you today. Then we will get a basic understanding how this works. So we can get some plots like this. So lot of things can be done in simulation. So I will go through with this example a little while later. So we will look at the theory step again. So I was here talking about what's happening behind. So we have the CAD model. We can apply fillets and all these things and model this. But when you have fillets and other unnecessary things in the CAD model, you will take it will take a lot of time to solve the answers. So these fillets, if you really need these fillets, include them in the model and do the mathematical modeling. Otherwise, have only the important fillets. So these fillet and the bottom fillet here are really important. So we keep them and we have removed the others. But since this is a simple model, we may not need to remove these things. But in complex design, like when you have a lot of parts, this will reducing these will reduce the calculation time a lot. So if the model is very complex, your calculation will take a lot of time. So that's why we are having a simplified model. And if your mesh is also very fine mesh, it will take a lot of time to solve the model. So it's up to you to get this optimum element size. So what do you mean by elements? So when you get a CAD model, this kind of mathematical model, we are going to discretize into small elements called uh, small elements. So those elements are in different shapes. So in SolidWorks, they talk about elements like tetrahedral elements. So this is a element shape. This shape is a tetrahedral shape. So this is called first order tetrahedral element, and this is the original shape. So when you apply some forces, this element will get some distortion. So what happens when you apply some forces? It will deform. So it will elongate. It will stretch. So the element shape will get changed. So what do you mean by tetrahedral? I hope everyone knows the shape of tetrahedral. So it's like a pyramid. So this is the tetrahedral shape. So it's like a pyramid, but the base is a triangle. So we have a lot of four triangles, 1, 2, 3, and the other side 1, 4. So this is the tetrahedral element. Uh, so something like these kind of things. So when you get a model, CAD model, SolidWorks will divide the CAD model into lot of tetrahedral elements. So each and every element he will write a equation. So he will write a equation and he will try to solve the equation. So that's what I have explained here. So we have the tetrahedral elements. We are going to apply some loads and the element will get distorted. But here we have said that this is a first order tetrahedral element. First order means I hope you know about the orders in differential equations. So if you don't know anything, let me know. So this is a first order differential equation. So he is going to write a first order differential equation for this tetrahedral element. So I hope you know about the order. So this dy by dx dxy equal to qx. So here the order is 1. So if you just look at second order differential equation, this is a second order differential equation. This is a first order differential equation. So in SolidWorks, they will deal with only first order and second order differential equations. That is, they are going to write differential equations for each and every element. So when you have first order elements, he will write first order equations. When you have second order elements, he will write second order equations. So when you uh, when you have second order elements, what is the advantage over first order is it can take these kind of complex curves. So when you have a model like this, when you have a hole, if you try to model this using first order tetrahedral elements, there will be not 100% matching. So the whole shape cannot be taken 100% because the first order elements are what? Straight lines. So the first order elements has straight lines, but the second order element has curves. So when you try to model this kind of a shape using second order elements, the modeling is much more accurate than this one. So because there is a hole here, this has a curve, circular shape. First order guys cannot take that exact circular shape. What you can do here is you can reduce the element size and try to match the circularity as much as possible. But when you try to reduce the elements, you get lot of elements in the model, then it will take lot of time to solve the equations. Without doing that, we can directly apply second order elements and get these curves correctly. So if you try to model these kind of curve shapes, these areas should be filled with second order elements. These areas can be filled with first order elements. So you can have two different elements in one model. You don't need to have all the areas second order, because second order, these areas we don't need to have second order. But here this area we need to have second order. This area we need to have second order. This area we can have first order. So it's up to the engineer or the person who is modeling to give these kind of correct inputs to the software. So this should be fine-tuned to second order. These areas can be used can be dealt with first order. So these areas first order. So I hope you understood the meaning of second order and first order. So the second order element has lot of these dots are called nodes. Lot of nodes are there. Here only 1, 2, 3, 4 nodes. Here after deformation also the same nodes will be there. Here if you look at the second order, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 nodes. So you have a lot of flexibility in second order elements. So when you work with SolidWorks, normally in complex modeling, we use the second order elements. So I hope you understood this. Let me know if you don't understand the theory. Then so we have the this is called solid model. That is, if you have a solid model like this has a thickness, so we have to apply solid elements. So one of the solid element is called tetrahedral elements. But some models are there which doesn't have a thickness, which has a very tiny thickness, very small thickness. So if you have something like this kind of model which has a very like a paper kind of a thickness, say if you try to model a say sheet metal, very little thickness. So you don't need to worry about solid elements. You can go to shell elements. So there's another element type called shell elements in SolidWorks. So shell element doesn't have a big volume. It's very thin. So if you look at my notes here, I have mentioned created by machine surfaces or face of solid geometry used to analyze thin wall structures. Triangle elements are the only type of shell elements in SolidWorks. So these are limitations in SolidWorks. Okay, so don't try to remember this one for other software. So other software will have different conditions, different elements. So this is only for SolidWorks. So you have second order, first order, and the second order. So here also, this is the first order shell element, this is the second order shell. So when you try to model a ring kind of a shape, circular shape, you can see the first order element is not taking the correct shape. But if you look at the second order element, you try to get the correct curvature accurate. So when you have sheet metal modeling, sheet metal finite element analysis, you can go with these shell elements. And there's another example. So this is a solid model, tetrahedral elements. Same, this is a second order shell element. So if you have a solid model, go with the tetrahedral solid elements. Otherwise, if you have a very less thick model like a sheet metal, go with the shell elements. So you can see the difference. So solid elements has a volume here. Shell elements actually don't have a volume. So then we have beam elements. So if you try to analyze something like a structural column or a beam, go use these kind of beam elements. So this example is when you have a I beam. Everywhere in the I beam, the shape is same. So you don't need to put lot of tetrahedral elements to model this. You can just simulate using a line instead of tetrahedral elements. So it says a beam element is a line with assigned properties of a beam cross section as required by beam theory. This illustration conceptualizes how a curve, here a straight line, defines an I-beam but does not represent actual geometry of the beam cross section. So when you try to model, say, welding structure or a building structure, a lot of I-beams are there. So I don't need to put lot of tetrahedral elements and model that. So you can just use the beam elements in SolidWorks, and beam elements will have only a line, representation of a line, and quickly we can model it. So so I may not go through all these things in the syllabus. We have applications related to these things. So if I have time, I will show you how to go through these I-beam simulations. We may do. So I cannot guarantee. It depends on the time we have. So remember, there are three basic elements. One is the solid elements called tetrahedral. Then the other one is called shell elements. Then last one is called beam elements. So any questions up to this? So when you get a model, you have to decide whether I'm going to use solid tetrahedral second order or first order, whether I'm going to use first order, second order shell, or whether I'm going to use beam. Any questions about this? you are not following me or cannot understand, let me know. Actually, I am just without doing lot of theory, I'm just trying to map the finite element analysis to the SolidWorks software. So that's what I'm trying to do here. Um, so now we discuss about 3D elements. So all these are kind of 3D elements. Even though this has a very low thickness, it's a 3D element. So if you want to reduce your time, the modeling time, you don't need to go behind all the time the 3D elements. So if you have something like this kind of a model or this kind of a model, which is a continuously, which has the same shape everywhere. So this has the same shape everywhere. This has the same shape everywhere. You don't need to analyze the entire model. You can only analyze a strip of the model. So this is a 2D element. So without analyzing the entire 3D model, I can just take a strip, 2D strip, and put some boundary conditions and mesh it and analyze. So this will greatly reduce your calculation time. So if you have something like this kind of a axisymmetric object, we don't need to model the entire thing. So you can take only a strip like this and apply the boundary conditions and quickly get some results. So these are really important when you do a lot of complex designs. So not here we may not see a big difference because this is simple geometry. But if this geometry has a lot of connected objects and other assembly parts, if you try to model the entire thing unnecessary, it will take some time. So that's why people are using these axisymmetric properties and try to simulate it quickly. So I hope you understood this. So if you have a wheel kind of a shape, you don't need to model the entire wheel. You take a strip of the wheel and apply some 2D elements and solve. So we will try to look at these kind of examples also in our class when we do the simulation. So this is the basic idea. So SolidWorks so all these are for SolidWorks, please remember. This table is for SolidWorks, not for the other software, but lot of softwares will use this tetrahedral elements. Say if you look at ANSYS, they will also use these tetrahedral elements, but the application may be a little bit different. So remember, this is for SolidWorks. So we have 3D elements, 2D elements. We have first order elements as well as second order elements. So the first order element answers are not really accurate as second order. Second order answers are really accurate. So if you can see, this is the element shape in the first order solid element. So in the second order, it has a lot of nodes and it can take the deformed shape accurately. And shell elements is just a triangle shape in first order, but in the second order, it has more nodes and it has some curvature. And beam elements, even in the first order, the second order, it's the same shape. So beam means don't think this is the element shape. Element shape is like a straight line like this. So they try to model all the welding structures, everything using a line. So then it will reduce the calculation time a lot. Then we have 2D elements. So 2D elements doesn't have volume. It only has some area. So when you have something like these kind of models, you better do it with 2D elements. So this is the basic idea in our lecture series. So when you get a model, you have to decide whether I'm going to use second order or first order, whether I'm going to use 3D elements or 2D elements. So if you go with 3D elements, whether I'm going to use solid elements, shell or beam elements. So beam elements normally for structures. Shell elements are for like sheet metal. Solid elements are for objects which has some volume. So this should be remembered. This table should be in your head to apply the correct mesh. So any questions up to this simulation elements? Okay, so if you don't have questions, we will proceed. So I'm trying to uh, explain as simple as possible, because you may have not learned the mathematics behind this. So if you try to learn mathematics, it will be taking a lot of time. So we are directly jumping into the computer models. So we will look at what is happening actually in the behind. So actually what is calculated in finite element analysis. So when you get a model, I said we have a complex model. We are going to simplify the model. We are going to apply load, some boundary conditions, restraints, materials, type of analysis. So we can do a structural analysis, vibration, say, so what thermal analysis, fluid analysis. So a lot of analysis types are there. Then software will create the finite element model using the discretization. So I have to get the mesh, then it will give me answers. So what happens in the software in behind the software, what happens? So in a structural analysis, what he does is he tries to find the displacements. So he first tries to find this displacement when you apply some load. So for an example, mm, the second lecture, what we are trying to do here is we will do this example, then you will quickly understand what I'm telling. So these are three different tests we have done. So after I have done the test, you can see the element size is 11.54 millimeters. Then the element size reduce. So we have done the same. We have applied same loading conditions, and we have fine tuned the mesh. So when you fine tune the mesh, you will get displacement values. So this is the value software will calculate. So what is the displacement due to the loading? So based on this displacement, what he does is, I hope you can remember, if you have done A-level mathematics, A-level physics, this kind of a curve. So you may have learned what stress strain curves. So what he tries to does is he tries to calculate. So first he tries to calculate the displacement. He tries to calculate the displacement. So after he calculates the displacement, he can calculate what? Strain. So you may have heard about this equation. So he tries to calculate the displacement, and if you know the original length, you can calculate the strain. Okay. So if you know the displacement, if you know the original length, you can calculate the strain. So after you calculate the strain, what happens? Here we can calculate the stress, because using the Young's modulus. So what is that equation? So we can calculate this kind of a strain Then if you know the Young's modulus, if you know the Hooke's law, we can calculate the stress. So that's what happening here. So he will calculate the strain. So every material has a Young's modulus. So he will multiply the strain by the Young's modulus and get the stress. So that's what happening behind the scene. So you calculate the displacement first in the software internally, then using the delta L over L equation you calculate the strain, then using the Young's modulus you calculate the stress. So that's the sequence of calculations. So first calculate the displacement, then strain, then stresses. So you have to make sure your materials are following these kind of curves. So normally in A levels we have discussed this curve. So the Hooke's law applies only for this area. So we have to make sure our materials doesn't go beyond this. So otherwise, if our loading conditions go beyond this point, yield point, it will be a permanent deformation. So we assume our loading is inside this one. But when you apply some loads, we don't know whether this will be in the elastic region or this may go to plastic region. So if our model goes to the plastic region, we cannot use these normal equations, so you have to go to nonlinear methods. So SolidWorks has nonlinear methods also. So in the first few lectures, we will look at the linear methods only. So I assume my curves are always linear and it follows the Hooke's law. So we calculate the strain and we multiply it by the Young's modulus and calculate the stresses. So if your stresses go beyond this point, your model actually will get permanently deformed. So you have to make sure your model is within this region. Otherwise, when you remove the load, it will not come back to the original position. So I hope you can remember these things. So when you apply a load and after you release the load, your model should come back to the normal position. Like a rubber tape, if you stretch a rubber tape and release the rubber tape should come to the original size. So if the rubber tape is not coming to the original size, that means it has permanently went to this area, plastic area, and permanently deformed. And if you apply a lot of loads, ultimately it will get fractured, it will break. So in the first few examples, we are trying to work within this linear region. So you can work with the nonlinear region also when it comes to SolidWorks. So we will focus on the linear region first. So I hope you understood what happens behind the scene in structural analysis. In thermal analysis also the same scenario happens. We calculate the temperature of different areas and we calculate the temperature gradient and the heat flow. So you have a conduction equation. This is also done in A levels. This one. So we calculate the temperature and we can calculate the thermal temperature gradient and thermal conductivity depends on the material. Then we can calculate the power per unit area transported. So these simple equations will be used in SolidWorks also. So we will first calculate temperature, then the temperature gradient, then the heat flow. So in thermal analysis. So I hope you understood what happens behind the scene. So they will use those fundamental equations if those are linear. If the loading is linear, if the loading is non-linear, if it is go to the plastic areas, then we have to use non-linear equations. So for the first few examples, we will stick on to this linear area and study. So now when we get the results, we have to decide whether the model is going to fail or not. So there are two very famous failure criteria in stress theory. One is called von Mises stress failure criteria, and the other one is called maximum normal stress criteria. So the von Mises criteria is used actually in ductile materials. So if you remember your A levels, this is a behavior of a ductile material. Normally, all the metals, a lot of metals will follow this curve. So this is a carbon steel curve. So this is a ductile material. So the von Mises criteria is good for ductile materials. But if you look at stress strain curve for ductile material. So ductile material is the famous one. What we study in a lot of times in A levels is the ductile failure. So if you look at the brittle materials, this is the brittle curve. So brittle curve will not have this kind of changes. It will increase its stress with the strain, and suddenly it will break. So the brittle material doesn't follow this kind of a transition. For an example, if you think about glasses, glass is a brittle material. Glass is not going to deform like this. When you it will suddenly break. So when you uh, uh, just apply some load to the glass, it will suddenly break. It will not deform like this and break. So you will see some more curves. So this is another one. Ductile materials will have these yield points and the maximum UTS, ultimate tensile stress and fracture. Brittle materials just increase the stresses and suddenly breaks. So when you have these two kinds of materials, we have to use two different criteria. For the first ductile materials, we have to use von Mises stress criteria, and brittle materials, we have to use this normal failure criteria. So that's why we need to know about these kind of theory a little bit to interpret the results. So have you learned about these kind of stress theory in other subjects? Uh, any idea about that? Any output? Have you studied about mechanics of solids or mechanics of uh, strength of materials? Those subjects have you studied? Uh, Shear stresses, those kind of things. Have you studied about those things? No idea.
No, sir, we haven't.
Excuse me.
No, sir, we haven't.
You haven't studied about shear stresses, those things.
Oh, in this course, we haven't.
You know about normal stress and shear stress.
Yes.
Okay. So uh, now in von Mises criteria, this is kind of an element. So I told that our model is going to break into elements. These kind of elements. So every element has a node. So these are the nodes. So every node I can write, for every element I can write equations. So this is kind of an element. So when you write equations for the elements, so software will do it for you. But if you are doing it manually, you have to do all the things manually. You can calculate these stresses and shear stresses and normal stresses. So every element will generate these kind of normal stress results and shear stress results. So when you apply a load, so think that way, because I'm not going to deal with the mathematical equations at the moment. So he will generate these kind of you can calculate these kind of normal stresses and shear stresses, because actually we calculate the displacements. So depending on the strains and stresses, we can calculate the other values easily. So we will get all these 9 components. So every direction has three components. Three normal stresses, sigma x, sigma y, sigma z, and tau zx, tau zy. Likewise, shear stresses, six shear stresses, three normal stresses. So all these calculations can be done. Then what one Miser says is get the cumulative of all these things. So one Miser's equation is this one. So he will use all these 9 components and calculate an answer. That answer is called one Miser stress value. So we will look at this one Miser stress value and compare with our yield stress. So what happens here is I will get a value like, say for an example, 200. So we will get a value called 200 after we get these calculations done. So we are going to compare that 200 with the yield strength. So what I am going to do is I am going to apply some loads, and I am getting the one Miser's answer, say 200. So 200 may be here. Yield strength may be 300. So if your answer is 200 and if the yield value is 300, what is my conclusion? One conclusion is my model is not going to fail. My model is not going to deform permanently. So my model is under 300. So in steel normally it's 300 megapascal. So if you look at steel, it's 300. So if my answer is 200 using one Miser's criteria, my model is actually safe. So when you apply a load, it will deform, but it will not be permanently deformed. When you release the load, it will come back to the original location. So that one Miser's value will be compared with the yield strength. Then when your yield strength is higher than the one Miser's value, your model is actually safe with that loading condition. But suppose your one Miser's values are coming here, beyond yield strength, then what happens when you apply the loads, your model is permanently going to deform. So you cannot get back the original shape again. So that's why we compare this one Miser's with the yield strength. So it's a non-negative value, and we are getting this value from the software. So we have the yield strength from the material properties. So we compare yield strength and the one Miser's value. If the one Miser's value is less than the yield strength, your model is safe. If the one Miser's value is greater than yield strength, your model is at a risk. So then you have to do some fine tuning and try to get somehow the one Miser's value less than the yield strength. So you have to do some fine tuning and apply some fillets and other things and try to reduce your stresses as much as possible. So that's the basic thing we are trying to do under structural analysis in ductile materials. So in brittle materials also we do the same. So this is what I told earlier. So we are getting the one Miser's value. For an example, one Miser's value is 200. My limit is 300. Limit is the yield strength. Here, yield strength is 300. One Miser's is 200. So my factor of safety is 300 divided by 200. It's 1.5. So my factor of safety is more than 1. If my factor of safety is more than 1, my model is actually safe. So I hope have you heard about the word called factor of safety? So the factor of safety is calculated from the limit, sigma limit divided by sigma one Miser's. So sigma limit is the yield strength. So yield strength is this point. So in simple English, what we say is, if the one Miser's is somewhere here, your model is safe. If one Miser's is touching this yield strength, you are on the fence. That is, if the factor of safety is 1, you are on the fence. That is, you are exactly on the fence. So if the factor of safety is less than 1, you are not safe. So your model is not safe. So when you do a design, you have to make sure your factor of safety is as much as higher as possible. Say if it is 10, factor of safety is 10, it's a very good solid model. It won't fail. But the problem in our mechanical engineering or mechatronics is when the factor of safety is getting higher and higher, your model is getting bigger and bigger. That is, your model weight will be big, your material strengths are high. That means that your basically your model will get unnecessary weights. So if you are designing an aircraft, you can't go behind factor of safety 10 and 15 likewise. Then the aircraft will be very much higher in weight. You cannot fly it. So you may need lot of fuel to fly it. So in aircraft industry, the factor of safety is very close to 1. So it should be more than 1, but should not be less than 1. So when you look at civil engineering, the factor of safety may be 100. So because they don't care about the weights normally. So the weights is bared by the earth. So you don't have problems. When you try to design a vehicle, you cannot have a lot of factor of safety, then the vehicle will be heavy. You need to have a lot of fuel to burn. So this is a value to be decided by the manufacturer, but it should not be less than 1. If it is less than 1, there will be permanent deformation. If this is exactly 1, you are on the fence actually. If it is greater than 1, it's the best. So more the value of factor of safety is the best, but you have to think about the other weight problems, cost of fuel, other problems also. Okay, so this is all about ductile materials. But when you look at the brittle material doesn't show this kind of behavior. Brittle materials normally fail like this. So it goes and quickly fails. So this kind of a doesn't show this kind of a transition. So in brittle materials, we can't use this kind of a von Mises criteria. They have introduced another criteria called maximum normal stress criteria. So they will calculate all these normal stresses and use the normal same equation, factor of safety, and get the decide whether this is going to fail or not. So there is no big equation like von Mises. Von Mises has a big equation considering all the stresses and strains. In maximum criteria, we get the maximum stress, maximum normal stress, and divide this by yield ultimate tensile stress. Now here it's changed to ultimate tensile stress. Earlier it was like yield strength. So in brittle, we look at the maximum value here. In ductile, we look at the yield strength. So in brittle, we don't have this kind of transition. So we look at the maximum value. So if your factor of safety is less than 1, that is, if your maximum value is, if the factor of safety is less than 1, that means this is higher than this. That is, you have already failed your model. So in brittle materials, there is nothing called plastic deformation. If the factor of safety is less than 1, the model is failed. Model has a fracture. If the factor of safety is greater than 1, your model is safe. So when you apply different materials, you have to make sure you are using the correct criteria to decide whether the model is failing or not. So these are the two principal criteria we need to remember. Von Mises is for ductile, maximum normal stress criteria is for brittle. And any questions up to that point? So basically remember this brittle curve and the ductile curve. So in A-level physics, I hope everyone has learned this. This is a very famous curve. So we have to sit on this area always, elastic area. If you go to plastic area, your model is permanently deformed. In brittle materials, you don't have plastic elastic. It will go rise and it will fail. So that this is the difference. So it will suddenly breaks, brittle, ductile, it has a transition. So we have to make sure our models are inside this linear curves. So if it is going to non-linear areas, there will be problems. Then yes, FOS value should be greater than 1, but FOS value should not be very high value. That is, if it is 100, that is you have over designed your model, so you cannot have very big FOS values, factor of safety. Depends on the application you do. Say if you are doing a civil structure, no problems. They put lot of materials. They have over designs everywhere. If you look at civil buildings, lot of over designs are there. So people rely on lot of gut feelings. They think that there will be a quick coming, and they will think that there will be very say, thunderstorms will come and collapse the building. So they have a very big factor of safety. So, but if you are doing a simulation, you can actually reduce that factor of safety. So that's why we are doing simulations and try to optimize our model without wasting materials unnecessarily. So you can have, instead of having 2-inch thickness, we can have 4-inch thickness and increase the factor of safety. But in mechanical engineering, the problem is we will increase the weight. So when you increase the weight, there will be problems of fuel consumption and other problems will come. So mechanical engineering, we don't have that luxury of increasing the factor of safety as you wish. So if you just look at, there are some norms. Um, so these are some norms people should have. Uh, I will try to find a factor of safety values. So they give these kind of norms. So these are some norms, aircraft components. As I said, very little value, small value close to 1. Why the problem is, if you have lot of factor of safety, your model will be heavyweight. You cannot lift the aircraft. So balls 8.5, cast iron wheels, so 20. So depending on different components, whether it's very critical component, we have to have higher factor of safety. So life equipment hooks 8, 9, turbine components static, turbine components rotating. So these things are available in handbooks. So when you do a design, make sure you are following these kind of principles. So if you study about factor of safety a little bit, you can find these values from the internet even. So remember, there are criterias like this. Okay. So never goes below 1. If you go below 1, actually you have actually failed your model, failed or permanently deformed. Then these are the units we need to remember when we study these simulation areas. Everyone knows these basic units. We have I am going to use these SI units. in our simulations, we have the mass measured in kilograms, length measured in meters, time measured in seconds, forces newtons, gravitational acceleration is there, mass density is there, temperature is Kelvin, or if you want, you can interpret the results in Celsius also. So SolidWorks has the flexibility of moving between the units, no problem with the change in the units. Quickly we can change the units and interpret the results. Then yes, same about the units. So these are the curves I have discussed. So normally we assume our models are behaving in the linear range. If it is in the non-linear range, you have to use SolidWorks non-linear modes. So in the first few days, we are actually looking at the linear range. So there are limitations in SolidWorks. So if you have the premium version, there will be no problems. Everything can be simulated. Non-linear material analysis and dynamic analysis can be performed SolidWorks simulation premium. If you have SolidWorks professional, you cannot do non-linear analysis. So all structures and distance are assumed not to change with time. Dynamic loading cannot be analyzed with SolidWorks simulation problem. So dynamic loading means it changes with the time. But I think everyone is having SolidWorks Premium, so every test can be done. So you can actually do drop test in SolidWorks. That is, you can drop a model and see whether this is going to break. So you can freely drop uh, a model. Say for an example, I can model a mobile phone and drop it on the floor and see whether it's going to break. So those things are easily capable in SolidWorks. So any questions about this first lecture? So this is an example of a drop test. So we can model something like this kind of thing and can drop it. And after I drop it, I can see, I can generate these kind of sense outputs and see whether my model is failing or not. So this area is going to fracture, high stresses. So we have to do something about that. So you can drop the things under gravity and see whether these are going to fail or not before the actual production happens. So all the things can be done in simulation environment and verify your simulation results and do the actual production. Any questions about this theory? So basically you need to remember this one, this table. When you do simulations, automatically you will remember this. No need to by heart these things. So we have 2D elements, 3D elements, and first order and second order. Remember this is for SolidWorks. Then depending on the application, I have to use the correct element. Then we have two criterias. One misses is for ductile, maximum normal stresses for brittle. So no need to remember these equations. I will not going to ask write the von Mises equation. I am not going to ask those things. You need to just remember the factor of safety equation, and if the factor of safety is 1, more than 1, your design is safe. If the factor of safety is exactly 1, you are on the fence. If the factor of safety is less than 1, it's very dangerous. Your model will fail. So it applies for both the brittle and ductile materials. So the brittle materials, I have taken the maximum criteria, maximum principal stress criteria. So if you study these things in theory class, they will teach you all these things and you will write manual equations and do these things. So in our class, I am going to use software outputs and show you how to interpret these results. So, and we have linear and non-linear models. Materials also, we have linear and non-linear materials. So we will look at some linear models in this syllabus. So any questions before I go to the application? Okay, so I will start this application. Then you will get a good understanding about how to apply SolidWorks simulation in a CAD model. So we will do the static analysis of a plate, small plate. This is our application. So we have a plate here which has a hole, and I'm going to apply 100,000 Newton tensile load to this side, and this side is fixed. So how can I do this kind of a simple application? So I will open the SolidWorks software and show you how this should be done. So we have shared the part file with you. In chapter 2, so I have given a part file called hollow plates. So better you open that file, and we will see how it works. So I have given this part file called hollow plate. So I will open this. Now we have to first enable the simulation environment. If you haven't done enable this one, we have to first enable the simulation environment in SolidWorks, and we will look at what are the things available under simulation environment. So I will open the file. So I hope everyone can model this kind of simple file now. No problem with that. Now check whether your computer has this simulation area working. So if you right click, you should get this simulation. This is for structural vibration thermal, and there's a flow simulation also. So flow simulation we will do later. We have to use this structural simulation today. And if this is not there, you have to go here and go to tools, and under tools we have these add-ins. So under tools we have add-ins. We have to make sure simulation is added on. So you have to add this simulation. So you have two tick marks. One is for the startup, one is for the if you just untick this one, it will not start up, only add it. So better you put both the ticks here. In the later classes we have to use SolidWorks flow simulation also. So when you install the software, you have to give the serial numbers. So if you haven't given the serial numbers, you may not see these things. So if you have any problems with that, that means if you don't see this one, that means you haven't given the serial numbers when you install the software. So you have to actually put these things again, not the entire software, that simulation part. So I hope everyone is having this. So we can go to tools, add-ins, and enable this simulation. Later we need flow simulation also. Then if you enable this, you should get this simulation tab now. Okay, simulation tab here, as well as right click and simulation. Okay, so if you look at this drop down here, we have a lot of things. We have to define the study, what we do. We have to define the material. We have to do the loading, load the fixtures. Then we have drop test setup. Likewise, shell mesh, shell elements, machine types, running the simulation, plotting the things, getting tables, fatigue analysis. So a lot of things are there. And we have these options here also. So if I click the option here, I may see what are the things he is going to give me. So system options are there. Then we have default options. So system options, he will tell me what are the colors here he's going to use when he mesh the models. So the bottom of the face will be in red color. So these colors may be changed. So you can come here and change the color of the mesh. Simple. We will look at the other things later. Then we have default options. So the units I'm going to use. So here, if anyone is not following what I'm telling, let me know. So what I did was I enabled the add-ins here. Then I went to simulations here and options. So under options, I have default options. So we have to study this area a little bit. So I'm going to use SI units, and normally we get the displacement in millimeters. Normally don't put displacement in meters, because this is simple, very small outputs I'm getting. So small values I'm getting. Don't put it in meters, have millimeters. Temperature you can measure it in Celsius if you want. Then every time the output will be in Celsius. Angular velocity radians per second. Pressure, stress. So better you put this as megapascals. Normally this is the setting, but this is difficult to interpret. So we are used to megapascals. So better you put megapascals here. So then it's easier for us to interpret the stress values. Okay, so this is important, and Celsius may be good, better than Kelvin. Then these things we don't need to worry at the moment. We are doing high quality machine. So later we will discuss what are these high quality measures and other things. Results, later we will discuss what is this meant by V plus and other things. So we have several plots here. So when you do the static analysis, these are the plots is given. One measures criteria, then displacement values, then strain values he will give. When you do a frequency analysis, what are the outputs he is giving? When you do a thermal analysis, what are the outputs he is giving? When you do a drop test, what are the outputs software will show us? Fatigue, likewise non-linear, likewise. So if you want to add some plots, you can right click and add the plot. That is, if you need more plots, here say under static analysis I am getting von Mises plot. You can change it from here even. We can get displacement plots. We can get strain plots. If someone wants to get a factor of safety plot, you can right click and add the new plot and get the factor of safety plot is not available here. I will show you how to get the factor of safety plot later. We can get, say, first principle stress. So then I will get 4 plots by default. So those things are possible. Here factor of safety is there, factor of safety plot is there. So I will get factor of safety plot as the 4th one, or else I can delete it. So basically these 3 will be shown when you run a static analysis. So I hope you understood this. So we basically need this one units. For the time being, we have to remember what are the plots appearing. So we will look at now what are the studies we can do. So I went through this tools options and showed you simulations options and showed you what are the units we need basically, then the plots we are generating. Then we have here under simulation we have different studies. So if you just click on new study, you will find a lot of studies that SolidWorks can perform. So in our syllabus we will look at the static analysis basically. If I have time, I will just look at some other areas. So for the first day, we are looking at the static canvas. So you can give a name for your analysis, and if you are doing that kind of 2D elements, you apply 2D simplification. So for the time being, we will not do that. We will apply a normal 3D static canvas. So I will press OK. So once I press OK, your interface is going to change now. Here you have the model here, modeling features, and you have the static tab newly appearing here. So it says some hollow model name is given, then the connection type, then the fixtures, external loads, mesh, and the result. So your interface has now changed a little bit, and simulation is now showing these kind of buttons also. So we will discuss what are these buttons and these things now. Any questions up to this point? So when you do an analysis, make sure you create a folder and do these things, because there will be a lot of files created inside this folder. So after you save your results, there will be around 10 files additionally created. So still there is nothing created new, but when you apply the loads and other things, you will see there will be files created automatically. So better you have this in the folders and generate the results. So now first we need to apply some material. So I will go through the steps now.
Excuse me, sir. Can you show again how you get the simulation part?
You don't have this.
No, sir.
When you right click on this manager, can you see this button?
Simulation. No, I have simulation add-ins. It's there, but simulation is not
Yeah,
there.
when you go to tools here, tools under add-ins, did you find the simulation one? Tools, add-ins, you should see this simulation tick mark.
Rules එකේ add-ins කියලා එකක් පෙන්නන්නේ නැහැ sir.
You should go down. That is tools. You have to go scroll down a little bit. You have to click on this small arrow and go down. Then you will see the add-ins. Can't you scroll down? පල්ලහැටම යන්න බැරිද?
පල්ලෙහාටම ගියා sir.
Add-ins.
Add-ins කියලා එකක්. Right. Add-ins.
Add-ins. Then you have to check whether there's a button called simulation, SolidWorks simulation.
Right, sir.
So you have to make sure these both tick marks are on. And pro simulation later we need that. Pro simulation එක tick කරගන්න ඒක පස්සේ තමයි පාවිච්චි කරන්නේ.
Flow simulation. Right, sir.
someone cannot see this flow simulation and simulation, that means he hasn't installed the package. Serial numbers dala install karaganna ඕනේ එක හරියට. Okay, otherwise you
Right,
cannot.
sir. Okay. Good.
So after you do that, you should get this simulation button coming here and next to tools. It should automatically come. Then when you right click on this on the manager, command manager, you should see these simulations. Same thing. එතන තියෙන drop down list එකම තමයි මේකේ තියෙන්නේ. So if you want, you can hide this. මේක නැතුව මෙතනින් උනත් කරන්න පුළුවන්. No problem. Because this is a drop down list. This is a command manager. This is easy to navigate. This is a ribbon. So you can have whatever the things you want. Same thing. So if I do it from the beginning, just open the file. So when you open the file, this is normal SolidWorks modeling environment. Then simulation should be on. Always have these tick marks on, then the simulation will start automatically. Otherwise you have to come here and start again and again. Then simulation button is there. Here also the simulation is there. So you can go to studies from here or from here. So when you start a new study, you will see these kind of different studies. What we are going to do, we are going to start the static study. When you click on that, you will see the screen is divided into two now. So I have the model separately and the simulation separately. So here now we have to give these different boundary conditions and see what's happened. So first what we are going to do is we have to give a material. So how can I give a material to this? So in this application we are going to give cast steel as the material. So I will show you how to do that. Cast carbon steel. So in my notes also I have given you some screenshots. We have to give cast carbon steel as the material. So how can I apply a material? It's very easy. You can apply a material in the modeling even. So we have discussed how to apply a material here. So if you have applied material here, that automatically comes to the simulation. So if you haven't applied a material in the design stage, in simulation stage also we can apply the material. So how can I apply material? Right click on this and go to apply edit materials. So material library will be loaded. In our example, we need to apply cast carbon steel. So when we have a lot of materials here, so I will apply cast carbon steel. So cast carbon steel has these kind of properties. Some properties are in red color, some properties are in blue, some are in black. So red color means these material properties are needed for the static analysis. Red color means I need these properties for the static analysis. If you select a thermal study, these red colors may change. Blue means these are optional. Red is it's a must. To calculate these values, we need these red color values. Blue is it's optional depending on the plot you are going to output. Black means we don't need these parameters for the static analysis. So if you see something in red, those parameters are really important for the study. Blue means those are optional. Black means we don't need them for the study. So we don't need specific heat for the static study. We don't need thermal conductivity. We don't need damping ratio for these studies. We don't need. Okay. So we have to apply the material. So once you apply the material, the color will change and it will say cast carbon steel. Then our application needs to fix this side and apply 100,000 newtons for this side. So now the second one is called connections. Here we don't need to apply any connection. That is, we don't need to mount this in a spring base, or we should not apply any pin joints. So we don't need to apply bolts. We don't need to apply bearings for this model. This is a simple model, so we don't need to use these connections at the moment. So connection tab will be left alone. Here for this application I don't need, but I need the fixtures. So we can right click on this and apply a fixture. So we have fixed geometry, roller sliders, hinges, elastic support, bearings, bolts. So a lot of things are there, and advanced fixtures are also there. So I will try to apply fixed geometry to one of the sides. You click on that and it shows me a preview what is meant by fixed geometry. So if you look at the roller sliders, this is the situation. If you have a hinge, this is the situation. And if you go to advanced areas like symmetricity, so I told that we don't need to model the entire thing. If the object is symmetrical, actually we can have a symmetricity condition here in this example also. I don't need to model the entire thing. Axisymmetric, we have discussed this term in the theory. Reference geometry, so we can give different criterias, millimeter values, translational values on flat faces. So there are a lot of conditions we can give. So we will try to cover some of the conditions with some examples. So in our simulation class, actually I am using examples to show these different conditions. So we are looking at the first one, the easiest one, fixed geometry. So I'm going to click on this face and fix that face. So you can see a lot of small arrows have been created. I have fixed that face. If you want, you can change these symbols, and color can be changed. See, you can easily change the colors. Then we can change the symbol size even. So if the symbol is very big, you can reduce that. See, you can see how it changes. So I have fixed this side. Then press OK. Now this side is fixed. Then we have to apply some loads. So you have to right click on this and apply a load to the other side. In my application, it's 100,000 newtons. So in my slides, I have mentioned what is meant by hinge, what is meant by roller sliding, what is meant by user geometry on flat faces. So you can go through these slides and understand the conditions. Then I have to apply 100,000 newtons to this side. So we will apply that. Forces. I'm going to apply a force normal to the face. So the direction is wrong. You have to reverse the direction, and the value is 100,000. Okay, so this is a uniform distribution. If you want, you can have non-uniform distribution, and you can change the colors, size of the symbol, and you can apply with not only normal to face, you can select directions and apply even. So you can apply in all these three directions. So for the time being, for this application, we are applying normal to the face. Okay, so these two conditions have been given. So any problems up to this point? So I have given material, I have fixed the things, and I have applied 100,000 newtons. to the other side. So I will save my model with the simulation parameters. So any problems up to this? So you can always go back to the model and do changes. If you do a change here, say now the material is not specified here. Say if I refresh, it should come, but it's not coming. Anyway, it's appeared here, no problem. So you can always go back to the model and change the model, and the simulation results will accordingly change. So any questions up to this? So I have fixed the site. You can always come here and change it, edit definition, or you can suppress this loading condition. Edit definition, you can come back and change, and always you can right click and change the definition of the load zero. So we will continue the lesson after the break. So have this kind of a thing ready, then we will mesh it and we will interpret the results, and we will fine tune our model and see how it should be done. So we have to discuss some more theories and try to fine tune our results and get a more accurate answer. So don't rely on the first answer. You have to get the optimum, most accurate answer from the software. So that's up to the engineer to do that. Software will not do it for you. We have to give our engineering inputs and get the optimum results. So we will do that in a while after the break.